Friends, let me introduce myself. I am Dr. C.S. P. Rao, working as a Professor of Mechanical Engineering in National Institute of Technology, Warangal. We have been working in this area for the last, say, 15 to 20 years. And as a part of the Computer Integrated Manufacturing lecture series, as a part of e-content development program, I am going to discuss today the important topic of CAM is computer aided process planning. Friends, you know the design. Design is taken care by computer aided design. Now the manufacturing is being done by computer aided manufacturing, and a very important link between the CAD and CAM is process planning, that is computer aided process planning. Always in any enterprise there are three very important departments. One is design department, second one is manufacturing department. The interlinking between these two departments is planning department, which is popularly known as production planning and control department. The role of production planning and control department is to develop process plans for the designed components. Unless you develop process plans for the components, the manufacturing people cannot understand. What is this process planning? Process planning is nothing but what are the manufacturing steps that are to be taken in order to convert the design into manufacturing. It consists of several things, not only selecting the processes. It consists of selection of machines, selection of tools, selection of timings, time standards, several other things. And one more thing is, there is no unique process plan. Process planning gives you several solutions. A part which is designed in one way can have more than one process plan. That means we can manufacture the component in more than one way, but there has been always only one method which is very optimum. Optimum in the sense, the method that gives you the best process sequences, the best utility of resources, the best manufacturing lead time. It comprising of several bests, and the best, that is the best process plan. But in a conventional manufacturing unit, the process plans done by human beings are varied numerously. Thus, there is no unique solution for this. And let us now discuss the various ways and means of the process planning and how it is being modernized or automated, which is known as automatic process planning or computer aided process planning. Let us have a detailed discussion on this in the coming slide. The 21st century engineering we are entering in, its response to the world competition is concurrent engineering. Concurrent engineering requires the integration of all aspects of the product life cycle, that is design, manufacturing, assembly, distribution, service, disposal. Two important areas in the life cycle of a product are design and manufacturing. Process planning serves as an integration link between design and manufacturing. Process planning consists of preparing a set of instructions that describe how to fabricate a part or build an assembly which will satisfy engineering design specifications. So let us now discuss the process planning in detail. It involves describing detailed instructions that one uses to fabricate a part to specifications. The instructions include operation sequences or the processes, the tooling and fixtures to be used, inspection methods to be used, gauges to be used, and the graphical representations, etc. Process planning is an act of preparing a detailed processing documentation for the manufacture of a piece part or an assembly. Systematic determination of the methods by which a product is to be manufactured in economically and competitively. These are all various ways that we can discuss the process plan. But we often confuse with two words. One is process planning, the other one is production planning. In fact, the process planning is entirely different from the production planning. I am going to give you those things here. Process planning is concerned with the engineering and technology issues of how to make the product and its parts, what type of equipment and tooling are to be used to fabricate the parts and assembly the product. Whereas production planning is concerned with the logistics issues of making the product, that is ordering the material, ordering the tools, obtaining the resources requiring to make product in sufficient quantities to satisfy. It may be noted that always production is done only after the process planning. There are certain decisions included in the scope of process planning, that is interpretation of design drawings, and the process planner should have the knowledge of processes and sequences, and should have the knowledge of equipment selection and take a decision regarding that. And you should have the knowledge of tools, selection of tools, dies, molds, fixtures, gauges, and methods analysis, which include workpiece layout, small tools, hoist for lifts, heavy parts, hoist for lifting heavy parts, hand and body motions for manual operations, work standards, that is time standards for each operation, cutting tools, machining conditions and cutting conditions, etc. You see in this slide, it is simply a operation sheet. We can call it as a process plan, a routing sheet which indicates the operation codes, 10, 20, 30, 40, 50, they are all operation codes indicating 10 is saw to rough length, part is a valve for main tank, and it has been given certain numbers and other things, and material is 1020 carbon steel, and the various description of the operations are being given, and the machine to be used is 114. Like that, description of all the parts. The 10 is the code of the operation. We have to remember one thing, that you cannot go to the 20th operation, that is facing, without completion of 10. So this is the sequence of operations indicates 10, 20, 30, 40, 50. And the machine on which what are the type of machine, and tooling and setup time and cycle time for the completion of this part, everything is given. This is a typical process plan sheet. And this is a typical, for this part only the process plan is given. And the process plan indicates the routing sheet previously shown, and the drawing, this is the drawing of the drawing, and scheduling is also a sheet which is also be done along with the process plan. With all these details, with the drawings of the part and the details of the route sheet and scheduling sheet and process plan sheet, all of them put together will be sent to the manufacturing departments for the manufacturing people to follow the manufacturing steps in order to realize the component. So it is another typical process plan sheet being used in. This is more or less a standard one, but the format could be different by the different manufacturers. These are the typical process plans being used in industry. I'm just showing them for our reference and better understanding. If the process planner's productivity is significantly improved, Because process planning is one act which is based upon completely the process planner's view and his expertise and knowledge. Hence, if the process planning is done by one process planner, could be different from another process planner, and his time is very, very important. If he could save his time, he would be able to spare his time, remaining part of the time, on various other aspects in order to improve the productivity. He can spend more time on the methods, improvements, and cost reduction analysis. Routines can be consistently optimized. Manufacturing instructions can be provided in greater detail. Pre-production lead times can be reduced. Responsiveness to engineering changes can be increased. And the development of process plans involves a number of activities. First is part print analysis, which is called as analysis of part requirement. Selection of the raw work part, that means the basic shape and size of the workpieces. Determining manufacturing operations and their sequences. Selection of machine tools. Selection of tools, work holding devices, and inspection equipment. Determining machining conditions and manufacturing time. What is this analysis of part requirements? The part requirements can be defined as part features, process that includes the process determination steps of processes. Dimensions, it will take decisions regarding the selection of machine tool size. Tolerance specifications, the capability of machine tools can be selected based upon the tolerance specifications, and the CNC code generations, etc. And selection of raw workpiece. It involves such attributes as basic shape of the workpiece. You can have standard materials, whether it is a rod or a slab or a blank or a profile, and the dimensions. Pre-shaped, sometimes pre-shaped materials, cast parts, forged parts, extruded parts, like that. Size of the workpiece, basic raw material, and size of the machine tool, size on which this workpiece is capable of holding it, and material conditions, tool selections, other things. Determining manufacturing options and their sequences. Selection of the processes like availability, accuracy of requirement, suitability, and cost. Sequence of operations. There are several operations. What operation is to be done first? What operation is to be done next? Work holding methods. How best you have to work hold the methods so that maximum number of processes can be done on the given workpiece without change of setup. Cutting tools availability, cost of the cutting tools. You can do the operation with the least cost tools, and you can do the operations with the more costlier tools also. So all these things depends upon the process planner how he select it, and in which very important thing is selection of machine tools. Workpiece related attributes like part features and dimensions, dimensional tolerances, raw materials form. Machine tool related attributes, which includes process capability, size of the machine, mode of operation, manual, semi-automatic or automatic, CNC, if it is a CNC machine, CNC tooling capabilities, type of tool, size of tool, tool changing capability, manual or automatic. Production volume related information is also required. Production quantity, order frequency. You take here, there are several drilling operations shown here, which can be done on a drilling machine or a universal milling machine or a machining center, CNC machining center. You see here, it is a drilling operation. This is a core drilling operation. This is a step drilling operation. This is a counter boring operation. This is a counter sinking operation, and reaming operation, and center drilling operation, and gun drilling or deep hole drilling operations. All these operations can be done on a drilling machine, and the process planner should select the operation and select the tool for that operation. And for example, reaming cannot be done without drilling, so he has to select first a drill to drill a hole, and then reamer to ream the hole, and then if it's a tapping is to be done in the drilled hole, after that only, after reaming operation only, the tapping can be done. Like that, drilling, reaming and tapping must be done sequentially. You cannot do the reaming operation first, then drilling operation next, like that. So this selection of sequence of steps is a process plan. You take similarly turning operation. There are several operations that can be done on lathe machines. It's a simple turning operation, and you can see this is a operation, orthogonal cutting operation, and the tapering operation, profile turning operation, grooving operation, facing operation, face grooving operation, form cutting operation, boring operation, drilling operation, and several operations like parting, threading, knurling. All these operations can be done on lathe machines. So you have to select the machine and select the process next, and select the tool also for that operation. These are the milling operations, some of the milling operations, and select the cutter as well. So face milling operations, you have to use face milling cutters, and partial face milling operation, and this is end milling operation, profile milling operation, and pocket milling operation. These are all the contouring milling operations. There are several milling operations can be done on milling machine, like face milling operation, partial face milling operation, end milling operation, profile milling operation, pocket milling operation, contour milling operations. So the respective cutters can also be selected. All these operations can be done on milling machine. So selection of milling machine, and on that selection of process must be done, and selection of cutter must be done. So all these things have to be planned. And sometimes we have several lathe machines are available. What lathe machine must be taken, must be selected. So evaluation of machine tool alternatives. This can be done by machine tool capability. Machine tool capability, which is also called as process capability. So process capability has to be evaluated for all the machine tools that are available on the shop floor. So machine tool capability or the process capability can be done by statistical tests. You can see that after machining several components, let us say 100, 200 components in the same universe of discourse, and if you take the mean size and the deviations of that, plot them as a normal graph, and you can see the deviations in plus or minus 3 sigma levels, and accordingly you can calculate sigma, which is called as standard deviation, as under root sigma x minus x bar whole square divided by n minus 1, where n is sample size, or sigma is equal to r by d2. Machine capability can be calculated as 6 sigma by tolerance. Percentage means multiplied by 100. Machine capability less than 100 is capability is good. Machine capability more than 100%, it is not acceptable. So you must have to select the machine tool which is acceptable. Machine tool capability and process capability are inverse parameters. So process capability is 1 by machine tool capability, and process capability is nothing but tolerance divided by 6 sigma, and process capability is more than 1 means process is acceptable, and if the process capability is more than 1, if you have a choice of machine tools, you have to see the process capability is high, that kind of machine tool must be selected. And sometimes you can also select a machine tool based upon the unit cost of product. It is again a statistical test only. The distribution and size of finished parts are assumed to be normal. It can be done only by conducting some tests, some statistical tests, and the results are available on the shop floor, and the process planner should have these details before they start process planning activity. So they know the process capabilities and the cost of part being produced on a specific machine tool, all the things. So this is done by where ZU and ZL are the standard normal variates for upper and lower tolerance limits. TU and TL are upper lower tolerance limits, and mu is mean of the population, and sigma is standard deviation. And the portion of acceptable parts AP can be calculated as phi of Z of U minus phi of Z of L. where phi of z of u is the probability of parts having dimension less than the upper tolerance value, and phi of z of l is the probability of parts having dimension less than the lower tolerance value. So this is a typical process capability study, and how to calculate portion of acceptable parts. These are all already available, and this data is very much required for the process planner. Then the selection of tools, work holding devices, and inspection equipment. Tools, we have to select based upon the tool material, shape, size, nose radius, tolerances. Suppose if it is a single point tool, we have to select the tool parameters also, because the kind of tool signature or tool nomenclature that is required for a typical for processing of one kind of tool material could be quite different from the other kind of tool materials. For example, if you hole in a brass or copper, the point angle is less, okay, is sharp compared to drill a steel plate. So like that, the tool parameters or the tool signatures or the tool nomenclatures could be different. So we must have to select the tool material and tool nomenclature as well, depending upon the kind of workpiece which you are selecting, for which you are selecting the machining process. Work holding devices. The primary purpose of a work holding device is to position the workpiece accurately and hold it securely. Manually operated devices, they are collets, chucks, mandrel, faceplates. Design devices, power chucks, specially designed fixtures and jigs. Flexible fixtures used in flexible manufacturing systems like pallets and other things. Inspection equipment, online inspection equipment, and offline inspection equipment. And the planner also selects the cutting conditions and the manufacturing times. That is machining conditions. Machining conditions includes what is the cutting speed, what is the cutting feed, what is the depth of the cut you will select for one typical operation. So object is to set the cutting conditions in such a way that the economically best production state is achieved. That means the cost of machining must be high, must be less, and the cost of the quality of product must be very good. What is the economically best production state? It is one, minimum production cost to maximum production rate. Both indicates the same. Sometimes you have to choose the feed as feed, low feed or high feed. Low feed is finishing cut, and high feed is normally a roughing cut operation. You go for high feed. High feed gives you more productivity, more metal removal, thereby more production rate. And feed rate is not effective as cutting speed over tool life, and therefore feed should be set to maximum possible value. This is called as golden thumb rule of metal cutting. You must have to choose as high feed as possible in rough cutting operation. Limitations are maximum tool force that the machine or the tool can stand and maximum power available. Choice of cutting speeds. You can select high speed or low speed. High speed will give you low tool life, high tool cost, high production rate, shorter production time. Low speed, high tool life, low tool cost, low production rate, long production time. And sometimes you can also calculate minimum cost per piece. Minimum cost per piece can be calculated as sum of the non-productive cost plus machining cost plus tool changing cost plus tooling cost. So this is a popular equation which is available in any of the metal cutting textbooks, and particularly prefer machine tools by Jeffrey Boatwright has discussed all these things in detail. Cu is equal to C naught T1 plus C naught Tc plus Co Td Tc by T plus Ct Tc by T. So the other parameters have been given here. We can calculate the total cost of the component by this. For a single pass turning operation, Tc is equal to pi Ld by Vf. We know the Taylor's equation for tool life, Vt power n is equal to C. where V is cutting speed and T is tool life, N is stylus exponent, and C is cutting speed for 1 minute of tool life. Combining the above equations, one can get the cost per piece equation like this. This equation can be further optimized. Differentiating this equation with respect to cutting speed and equating to 0, then solving the cutting speed will give you the cutting for minimum production cost. And similarly, maximum production rate, TU is equal to non-productive time plus machining time plus tool changing time, and TU can be calculated by this equation. And this is again by the differentiating TU with respect to V and equating it to 0, then solving for V will give you the cutting speed for maximum production rate. This is the cutting speed for maximum cutting production rate. And afterwards, manufacturing lead time can be studied, can be calculated as lead time is equal to S plus TU multiplied by Q. Q is lot size, TU is equal to production time per piece, and S is equal to major setup time. If you know these things, we can calculate these machining parameters, and you can select the cutting speeds, you can select the cutting feeds, and accordingly lead time also can be calculated. And here is a small example given here to get much more clarity of the topic. A lot of 500 units of steel rods of 30 centimeters long and 6 centimeters in diameter is turned on a lathe machine at feed rate of 0.2 mm per revolution, and depth of cut is 1 mm. The tool life is given by this equation. The other relevant data has been given it here, and we were asked to determine optimum tool life and optimum cutting speed to minimize the cost, optimum tool life and optimum cutting speed to maximize the production rate, minimum cost per component, time per component and corresponding lead time, maximum production rate, corresponding cost per component and lead time. And you can calculate the relevant parameters which were given in the previous equations using the values given in this problem. As C0, you can calculate it, and we got it as $0.25 per minute. CT is equal to $5.16 per edge, and T minimum we got it as 84.56 minutes, and V minimum we got it as 82.3 meters per minute, and T maximum is 2 minutes, and V maximum is 174.1 meters per minute, and minimum cost TC is equal to $3.4 per piece, and CU is we got it as $1.2 per piece, and time per component can also be calculated, and maximum production rate is calculated as 1.62 minutes per piece, and production time per piece is calculated, and cost for maximum production rate is calculated as $4.82 per piece. And we know after this example we can easily conclude that we can select the speeds and feeds in such a way based upon what we want. Suppose we wanted to have higher feeds, the cost of production part is to be minimized, the speeds and feeds are selected. If we wanted to have maximum production rate, the speeds and feeds are to be selected differently, and tools are selected differently. So based upon this machining knowledge, the process planner should select the optimum speeds and feeds and depth of the cuts based upon the tool and workpiece combinations. Now, what are the various process planning approaches that are normally adopted here? One which is being adopted anciently is manual or experience-based process planning method. Even today it is popularly used. Second one is computer aided process planning method. Let us discuss these things. Manually method or experience-based process planning method. This method is most widely used method, but it's time consuming because it is completely depends upon the human planner and his knowledge and his experience, and it leads to give inconsistent plans. Today, if I am the process planner, if I do the process planning activity today, it would be like something, and if I do it after a few days, I could do another process plan. Both process plans are correct in all aspects. If you adopt this process plan or that process plan, give you the best component. But the sequence of steps and other things followed in one plan could be different from the other plan. So most inconsistency, this activities and most inconsistency. This can be, you can have only one kind of process plan if the part is so simple. If the part is complex, that means many number of machining features are there on the part, then we can say that the complexity of the part is increasing. And if the part is complex enough, then we may have to have more than one process plan. That means more than one plan can be generated, can be written. That's why in manually experience based process planning system, we'll have inconsistency in plans. It requires highly skilled and knowledgeable persons. It all depends upon the experience of the process planner and his knowledge base. Manual approach to process planning. Its use is still very widely spread in small to medium sized companies, especially in the aerospace industry. It involves subjective judgments reflecting the personal preferences and experiences. Plans prepared by different planners for similar parts are usually not identical. Very labor intensive, like 40% of task, involves preparation of documentation. Process planning activities in a schematic way is like this: analyze the part requirements, determine operation sequence, and select the equipment, and calculate processing time. And this is an iterative procedure. Calculate processing time. If this is more or less, again select new equipment, like that, and decide the equipment, and then document the process plan and communicate the process plan to the shop floor people. Factors affecting the process planning activity are volume of production, the skills and expertise of manpower, delivery dates, the schedules, material specifications, accuracy and process capabilities of machines, accuracy requirements of parts and products. Because of these variations, we need to go for automating the process planning activity. Can we do the process planning activity computerized or computer augmented process planning activity? Yes, it is. It is required to develop computer aided process planning or automatic process planning in order to have consistency in process plans and to reduce redundancy in process plans, to reduce time of preparation of process plans. We need to go for automated process planning activity. Particularly in the age of computer integrated manufacturing, we don't have any other option except to computer aided process plan in order to link the computer aided design and computer aided manufacturing departments. Process planning provides the link between CAD and CAM. Process planning function converts engineering designs into fabrication instructions. Thus, automated process planning is key to integrate CAD/CAM. Of course, the computer integrated manufacturing. Without automated process planning, CIM would not be possible or would be impossible. Both group technology and computer aided process planning are two essential elements of CAD/CAM integration. We already discussed what is called as group technology, and the group technology provides a basis and methodology for D&M, design and manufacturing communications, whereas automated process planning provides a means to facilitate this common communication and remove the wall between the design and engineering. SIM cannot occur until the process is automated. Consequently, automated process planning is the link between CAD and CAM. You can see this through this diagram. The need of CAD, the shop trained people who are familiar with the details of machining and other processes are gradually retiring. The experienced process planners are gradually retiring, and there is a gap, a tremendous gap of knowledgeable people are not there much, and depending on them is also very difficult. and several other options as we have discussed already. We have to go for automated process planning because of the need. There are certain potential benefits of the automated process planning, which includes 50% increase in process planning productivity, 40% increase in capacity of existing equipment, 25% reduction in setup costs, 12% reduction in tooling, 10% reduction in scrap and rework, 10% reduction in shop floor labor, 6% reduction in work in process, 4% reduction in materials. Other benefits include process rationalization and standardization. CAP leads to more logical and consistent process plans, lower manufacturing cost and higher quality. Increased productivity of process planners, more work to be accomplished. Reduced lead time for process planning. Improved legitimacy, computer prepared route sheet are neater and easier to read. Incorporation of other application programs, CAP can be interfaced with cost estimation and work standards. In a typical industrial situation, how the process planning activity is done is, let us say, computer-aided process planning activity is done. This is the CAD. For this, the design is this. This design information is available here. And this design information, in order to manufacture this component, we need to write a generator, a CNC part. This is the cutter path. Part code is need to be generated. And it can be done by human beings or can be done by CNC if you prepare CNC program. So again, if we ask why to automate process planning, shorter lead times, manufacturability, feedback, lowering the production cost, consistent process plan. In this slide, you see the design information is converted into manufacturing features. That is, for this we need to do workpiece selection, process selection, tool selection, feed selection, operation sequence selection, setup planning, fixer planning and part programming. How to do the CAP, computer-aided process planning, how to achieve? There are two varieties. CAP can be done in two ways, or two approaches are there. One is called as retrieval or variant computer-aided process planning system. The other one is called as generative computer-aided process planning system. Sometimes the two systems combine and known as semi-generative computer-aided process planning. Let us see what is this variant process planning approach. This variant process planning approach is a group technology based approach. It is based on group technology and process PCC, dependent on good data mining and search engines. Variant CAP system requires a database containing standard process plans. A standard process plan is stored in computer files for each part code. The standards are based on current part routines in use in the factory or an ideal plan prepared for each family. System has provisions for editing a particular standard plan to accommodate product variation. In the variant CAP method, process planning is developed for a master part or composite part, which represents a common features of a given part family. In the variant CAP method, process plan is developed for a master part. Master part is one which is having common features of a family of parts. Suppose if you have several parts of a family, all the features of these parts the master component have. So if a master component has got one feature, that feature must be present in one of the parts of that particular family. A process plan for a new part is created by recalling or identifying and retrieving an existing plan. Just by doing some editing operation of the existing process plan, we can generate the process plan for the new part, and we can do certain modifications for the new parts, and we can again store the new part process plan against the GT code. To use method, efficiently, parts classification coding system must be used. So we need to have a very good parts classification and coding system in order to have very good variant cap system. So in a nutshell, the entire schema of the retrieval cap system or variant cap system is presented here, in which a new part design for which we need to develop the process code. For that, first of all, when the part design comes, we need to derive the GT code, group technology code, and against the group technology code, search for the part family file containing the GT code. So we need to have a part family file in which the GT code is searched. Retrieve if the plan is existing, the same GT code, you retrieve that, or retrieve the nearest code. That means nearest part process plan of a part is to be retrieved, and do the editing operation, edit the existing plan or write the new plan, so which is easy because only few features are different. So edit the process plan and develop a new process plan and put them in the order, and the process plan format prepare the other application programs. So part family file is required, standard process plan file is required, and the coding system is required, and preparation of standard process plans for part families is also required. So these are all in order to develop a cap system. These are the preparatory stages like selecting code system and prepare standard process plans for the part families. Suppose you are going to develop a variant system which is suitable for few part family. For all those part family parts, you need to develop the GT codes and their respective process plans and store them. This is a preparatory kind of study. You have to do it before you start working for the new part program, new process. In order to develop the process plan for a new part, you need to do these preparatory stages. Cap system, again, GT code to form part families and create standard process plans for this family and store them in a database, and process planner code and classify new part into the family and retrieve the standard plans like that. And the data files that are required is steps in the preparatory phases are selecting the appropriate classification and coding system for the company, forming part families for the parts produced by the company, preparing standard process plans, and you have to repeat the above 2 and 3 steps as new parts are designed and added to the company's database. Capacity to alter an existing process plan. You can see this table containing different variant process planning systems that are available in the literature, and that are available, some of them are available in the commercially also. Cut plan, cap, ComCap, D-class, IntelliCap, MakeCap. These are the systems and the company that is developed, and decision logic are the function that are based you have given in this slide. This slide is a self-explanatory. Let us discuss the advantages of retrieval cap system. Once the standard plan has been written, a variety of parts can be planned. Comparatively, simple programming and installation is required to implement a planning system. Efficient processing and evaluation of complicated activities and decisions, thus reducing time and labor requirement. Standardized procedures by structuring manufacturing knowledge of process planners to company needs. Lower development and hardware costs, shorter development times. Efficient processing and evaluation of complicated activities and decisions, thus reducing time and labor requirements. Standardized procedures by structuring manufacturing knowledge of the process planners to the company needs. Lower development and hardware costs, short development times. Disadvantage of variant process planning system. Maintaining consistency in editing is difficult. It is difficult to adequately accommodate various combinations of material, geometry, size, precision, quality, alternate process sequences, machine loading, etc. The quality of final process plan generated depends on, to a large extent, on the knowledge and the experience of the process planner. The system is understandable. The planner has control of final plan. It is easy to learn and easy to use. Drawbacks are the components to be planned are limited to similar components previously planned. Maintaining consistency in editing is difficult. Experienced process planners are still required to modify the standard plan for a specific component. Now let us discuss the generative computer-aided process planning system. An automated computerized system is used to generate each individual process plan automatically without reference to prior plan. It is an automated computerized system used to generate each individual process plan. It does not take the database of the process plans and edit them like variant. Any part for which you need to develop the process plan, it starts from the scratch. So process planning is done automatically without reference to prior plan. The system consists of decision logic, formula, technological algorithms, and geometry-based data. The computer automatically generates a unique operation and root sheet whenever a part is ordered. Instead of retrieving and editing an existing plan containing in a computer database, it creates the process plan based on logical procedure. The process sequence is planned without human assistance and without a set of predefined standard plans. Expert systems and artificial intelligence algorithms have been used to develop generative process plans. Expert system is a computer program that is capable of solving complex problems that normally require a human with years of education and experience. First ingredient, technical knowledge of manufacturing and the logic used by successful process planners must be captured and coded into computer program. Knowledge and the logic of human process planner knowledge base is developed. The generator system then uses that knowledge base to solve process planning problems. Second ingredient for generative cap is computer compatible description of part is to be produced. Pertinent data and information needed for the plan. The process sequence, two ways is geometrical model like CAD or GT code. Third ingredient is capability to apply the process knowledge and the planning logic contained in the knowledge base to a given part description. CAP uses its knowledge base to solve specific problem, planning the process for a new part like inference engine. By using knowledge base and IE, it synthesizes a new process plan from scratch for each new part it is presented. You see some of the generative process planners that are developed and available today have been listed out in this slide. You can see E indicates that is experimental, C indicates commercial, and the part data input is G indicates geometrical, D indicates design. You can give input as design, and decision logic is by means of decision trees are used in APAS, APPAS, which was developed by Arya Wisk in Aachen University in Germany, and this is used decision tree, and it is used for H kind of shapes, means the holes, and R for rotational parts, B for rotational and non-rotational parts, like that. The details have been given in this all commercial and C, and this table gives only information about the availability of the process planning attempts, generative process planning attempts or systems limited to certain type of parts only, like rotational parts and hole making operations and certain things like that. But there is no unique generative process planning system developed so far which can address the problems of prismatic parts as well as rotational parts. However, the study on generative process planning is still continuing. The structure of a generative process planning is like this. Let us say start or a new part, component representation module. You can develop the component representation, that means input to this by means of the geometry means CAD. You can use the computer aided design details, which consists of geometrical details, or sometimes you can give the part geometry creation also. You can create in a user defined way. You can create the geometrical details and give it as an input to this. And if it is an old part, copy existing part or geometry file to the geometric file and do editing, and the editing module is there. And once that is over, the operation extraction is done by the sequencing module. And operation extraction, intermediate process, dimension computation, and operation sequencing. These operation sequencing algorithms are required here, which gives you prioritize the operations and sequence their operations. And selection of the machine tool is to be done. Machine tool selection module is available. So a huge database of machines tools availability and machinability conditions that are available on the shop floor must be available in the form of a database, and the database will be interacted with this module, and the necessary data will be extracted from the database. Standard time and cost computation module. We have to have a library of standard times for all the things in order to calculate the machining times, cost calculations, etc. And then report generation module, editing, modification and printing, and the process plan is ready. Components of the generative computer aided process planning consists of description, component characteristics, geometric features, dimensions, tolerances, and surface conditions. A subsystem to define machine parameters. A subsystem to select and sequence individual operations. A database of available machines and tooling. A report generator. Let us just discuss the generative CAD system in the form of steps. First step is input engineering specifications into the CAD system. That is part features which can be given like geometrical features, tolerances, sizes, locations, etc. Sometimes their coded information is stored as raw data in computer. Also describe the part in its rough state. It should be given as input. Ideally, engineering specifications should be captured directly from CAD file, and the current research is also that the CAD file is given as a direct input to the CAP module, and CAD file, the input may be in the form of .dxf files or PDES files or step files. The information is to be given as input to the CAP module. Step 2. Generate programs to transform coded data and textual information into a detailed process plan. Whatever the coded information is there or textual information, that will be converted and a process plan is generated. This requires complex algorithms and large databases to accomplish. Algorithms for sequence prioritization, algorithms for process selection, algorithms for machine tool selections, all of them are here included. There will be integration with the databases. It works with this reading the input file and understanding it, selecting the features, selecting the machining process suitable to the features, and prioritize the machining process, and select the machine tools for each machining process, and machine tool type and number of the machine tool from the database, and selection of the speeds and feeds from the database, tools for to machine the features, selecting all of them together and then listing them and then printing them in the form of a process plan. No universal generative process plan consists. There are some for special classes of parts with limited geometrical features. I would like to give an example process plan system which is called as computer managed process planning, CMPP. which was developed in United Technologies Research Center, and it's a commercially capable of automatically making process plan decisions with interactive capabilities. Interactive capability facilitates the user to examine and modify a process plans as it is developed. Developed specifically for machined cylindrical parts. The CMPP system is like this: interactive input, design system input, define part model, and part design file is created, and process decision model file is created. Planning logic is given and defined manufacturing logic through which process decision model file is created, and machine data and defined manufacturing resources machine data file is created, and perform planning functions. This is all given as input to the another subsystem of perform planning functions to generate the process plan. First, the databases containing specific information about the available machine tools, stock, removal allowances for cutting materials, types of cuts, tolerance, machinability, process decision module must be developed. Manufacturing logic and resources for a particular form should be developed. PDM technique is used to define local manufacturing rules. Rules defined by the use of COPPL, computer process planning language, you can use. It requires raw material, geometry, dimensions, final part shape, tolerances, surface finish, geometric form conditions, material specification, surface treatment. CMPP process planning functions are shown in this schematic, in which generate sequence of operations first from the part design data, then determine the reference surfaces and calculate dimension tolerances and machine tool data, and produce process plan documents. For each operation, operation number, description, type of machine, orientation of the workpiece on the machine, surfaces cut, and heat treatment are given. Dimensioning reference surfaces for each cut in each operation is defined, and machining dimensions, tolerances, stock removal for each surface cut in each operation is to be given. A printed summary of operations, a printed tolerance analysis, a dimension workpiece sketches for each machining operation is available. Now let us compare the two methods we have discussed so far. The two methods are variant process planning systems and generator process planning system. When you compare with respect to coding system, that means the computer programming, with respect to coding, whereas generator system is very detailed, variant system for part geometry is complicated, and if you have huge number of part families, and if you have a composite part, a complicated composite part is there, a variant is better. With respect to part geometry, variant is complicated, whereas generative is simple. Similarity between the family of components is very high, because if the part family, it is retrieved from the part families, hence the similarity of part component is very, very high. If it is dissimilar, variant will fail, whereas generative is best suited for dissimilarity of the component. That means it generates for any component any time. That means it generates the process plan from the scratch. So similarity between the family of components is very low. Family size, variant approach is very much used when you have large families of very few families, whereas generator system family size is small and number of families can be more. Database is a large database is having, because it need to search for a lot of group technology codes, and the database requirement is small databases only here. Investment and effort is high because a lot of pre-processing is required for the variant process plannings, whereas maybe low or sometimes is also high. Time to develop is very short for variant approach, whereas time to develop generator system is very long because of the programming complexities. Human intervention is very highly required for variant process plans, because at each time after retrieval you need to do editing operations. So for editing, human intervention is required, whereas human intervention is very required is very small here. Now let us discuss how to select a CAP system. The first point is to classification and coding capability. Classification and coding ability to change the part attributes, if you have process planning retrieval capabilities, would be very high. Second one is graphics capabilities. CAD database management, if it is based upon that, you can select either one of these methods. And third one is work instructions creation and maintenance, like word processing, text information, graphic storage, editing, global update, online help, form generation, automatic revision, history, and process planning capabilities, variant, generative, hybrid, or part family identification, capture knowledge of process parameters, selection of tools, time standard capabilities, calculation of standards, access to other vendors, standard time modules, and machining parameters, selection of speed, feed, determination of stock removal. These are all the parameters that you select for the process plan. And total system considerations like hardware requirement, database management capabilities, interface to other software systems, MRP, system cost, ease of use, future enhancement, vendor specifications. Selecting a process plan means define the objectives for CAP system, capturing manufacturing expertise and make available plan-wide. Reduce manual input in process planning, facilitate integration of CAD and CAM, develop optimum and consistent process plans. Specify criteria of CAP system, classification, coding capabilities, graphic capabilities, process planning features, work instructions, time standards, and other things. Based on this information, we can select the process planning system, available process planning system. You can represent the product representation as geometrical information, part shape, design features, technological information, tolerancing, surface quality, specific manufacturing nodes, feature information, manufacturing features. And this knowledge of the entire processes can be presented in the form of predicate logics and production rules, semantic nets, frames, object-oriented programming. All these things are being used in CAP system, in CAP programming things, and we need to do a lot of discussion in order to know that. So I'm not going into deep of these logic rules and other things, how to develop the process plan. We have only discussed what are the various process plans, but not how to develop the process plan. In this slide, some automated process planning efforts have been listed out. It's a self-explanatory, we can read on your own. And the developments of CAP, if you observe that from 1960 onwards, several attempts were done, and up to 2000 still the work is going on. Till today, we did not have a unique CAP system that can address all sort of computer-related problems. But today we have highly automated systems with a lot of intelligent and decision-making algorithms are imbibed in these systems. They can retrieve and certain attributes can be taken into decision logics, and decision-making algorithms are available. And with all that, an expert, some of the systems they give process planning as an output. But then a lot of research is still needed to be done, and whatever is achieved to the great extent only, and a lot of work is still concentrating particularly on the graphics interfaces and also on the intelligent algorithm, role of intelligent algorithm, on optimization algorithms, etc. Friends, with this I would like to conclude the discussion on computer-aided process planning. We have discussed the computer-aided process planning limited to the classwork knowledge only. I have not discussed in detail and the works which are going on in particularly in computer-aided process planning. There are several works, even NIT Warangal, we are doing particularly in using steps, databases, etc. We are developing several algorithms also. Several genetic algorithms and other fuzzy logic algorithms we have used to identify the features, and based upon the feature selection for the process planning generation. Such kind of works have been done using decision logics and predicate logics, etc. But we have not discussed all of them here. But friends, as a whole, we have discussed the importance of process planning, and then the types of process planning and the need and importance of the computer-aided process planning, and what type of process plannings are available, like variant system and generator system. If it is a variant system, what kind of knowledge is required to develop the variant system, and if it is a generator system, what kind of knowledge is required to develop generator systems. We have also discussed with CMPP as an example, and with this I thank you for all for your patient listening the topic, and a lot of we can discuss this elaborately also. Thank you for your patient listening. Thanks for the opportunity. Thank you very much.